All right, there are many types of regression analysis. We will learn one of the types, linear regression. The announcement discusses how to calculate linear regression, but I want to take a minute to explain why. Regression allows us to show if two or more variables have a relationship. For example, does diet and exercise have a correlation to weight loss? Is there a relationship between smoking and lung disease? Like I said, this week we're going to do what we know as linear regression. So back in algebra, we had the equation y equals mx plus b, where m was the slope and b was the y-intercept. Well, in linear regression, we have a formula that y equals b naught plus b1x. The reason to write it this way instead of y equals mx plus b, in linear regression we can do multiple regression where we can just put a 1 here on your x1, and we can add more variables to see if two or more variables have a relationship to something. So, to kind of show how this works, m is our slope, which is always going to be the value in front of the x, right? This is where we'll look to see if things have a correlation, and we'll get into this in a minute and how we can prove that. And then our b and b naught are basically kind of like a y-intercept. So if you remember back in algebra, x was the independent, and I'm going to run out of room, I always do, independent, and y was the dependent. Well, this is still the case in regression as well, but we sometimes call our x's now, besides the independent variable, we call them the predictor or the explanatory. And y is the response variable. So, still the dependent, but basically the y becomes how the variable responds to the things that we think have correlation. So let's talk about correlation for a minute. So there are many ways to see if there is correlation between variables. One way is to calculate the coefficient value. You can do this by using technology and StatCrunch. You can click on Stat, then Correlation, highlight the data, and then click Compute, and you'll get a value. For linear correlation coefficient is represented by the letter R, and there's some formulas on how to calculate that as well, but we will use technology to do it, and we will compare this to critical values. And there's tables for this in your homework. So basically, once you have a critical value, I can draw a left and right limit. So say our critical value is 0.858. So I can label this 0.858. I label this negative 0.858. So ugly 5. And then if my R value, say, is 0.23, well, remember, here is 0, so 0.23 would be somewhere about here. So my R is between these two values, so therefore, no correlation. Well, what if my R was 0.96, or even a negative 0.96? Well, 0.96 is out here, and a negative 0.96 is over here. It's outside of the bracket, so therefore both of these would have correlation. The only difference is this is a positive correlation, and this is a negative correlation. Alright, so another way we could do correlation is to build a scatter plot. So here would be our x, and here would be our y. So here is our predictor or explanatory variable, right? And then our y would be our response variable. So the Scottish plot shows a negative correlation, or a positive. A scatter plot is a great way to allow us to see if there is linear relationship. The points are plotted. They do not have to be in a perfectly straight line, just show that there is some linear relationship. So let's see if we plotted x would be amount time exercising, and our y value will be our weight, current weight. Right? So, we can do current weight loss. So, we can have some plots. So, I'm not going to put numbers to it, but we, have some numbers. Yeah, not that one. We want higher numbers, right? So, we're working out, and our plots are going like this. And we're keeping track of all the times we work out. Now, some of these aren't really good. Let's erase some of these. I want to show a relationship here. So there's some times, right? If we fit a line, kind of goes something like that, right? So I guess it wouldn't be weight loss, maybe our current weight. And as we continue to work out more, our weight drops. So therefore, a negative correlation doesn't always mean a bad thing. It can be a good thing. So I'm going to draw a couple better pictures here. So what we'll learn how to do in regression is we're going to learn actually how to calculate the formula for this line. And that will become our regression line. So, clean up my thing a little bit here. This is gone. I'll emphasize some points here so I can show why we need to do some things. So we'll get some good points. Right. And I'll just highlight these 4 points. Right. As we've done prior, we want to show things are normally distributed. Right. And everything we've done up to now, everything had to be normally distributed for this to work. So with regression, we have to show that our error is normally distributed. And so how we find error, it is the difference between, so E, 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 E. So the difference between all of our points, I only highlighted these 4. So you take your actual data point and you put that x value in, whatever it is, right, into your line, and you get a new point right here. My thing will actually draw where I want it to. There we go. And then we can find the difference between those 2 points to show how much error we have. And you can see, as on our picture, we have some error below, some error above. And what we want to know is if we plot all of the error, which is called our residuals, our residuals should show a bell-shaped curve, right? That they're normally distributed, which means the errors are kind of random, which is good, because if error is not random, then that means there's something causing the error, and then probably not a good thing to use a regression line to see, for make predictions. All right, once we calculate our regression line, we can do a hypothesis test, right? So, our hypothesis test, just like before, we have our null, and we're always going to base it off the slope parameter. And our B1 equals 0, or our alternative is B1 does not equal 0. And this is the hypothesis we always use. And the reason for this, remember, our B1 was our slope. So if we have a slope of 0, that's a flat line, and there's no relationship, right? We go back one slide, and you can see my line here, my green line, is decreasing as my x increases. Therefore, there is a slope in my line, right? Therefore, so this means if I have my alternative, my slope is not 0. Therefore, there is some correlation. All right, and the amount, the value of your B1 doesn't show how much correlation. It just shows how quickly your line is increasing or decreasing. Remember, it's your R value, your R squared, to show the right amount of correlation on a line. And one thing I didn't do very good last time, R and R squared is always from 0 to 1, right? That's how we show correlation. But we can look, before even doing all of our analysis, at a scatter plot. If we have a line like our green one, then we can start doing all these statistical tests to see how good our regression line is. So that's all our B1 tells us, is how quickly it's changing, not how much correlation something has, but it's how quickly something is changing. The sign on it does tell you if it's a negative correlation or a positive correlation, which will also be the same sign that's on your R. So if your B1's positive, your R is going to be positive. If your B1's negative, your R should be negative. Now, going back to our line, and you could, if you, again, want to build a confidence interval, that is fine too. And that way we can be 95% confident that the true B1 of this regression line is within the limits, just like we did before with confidence intervals. But our B0, so let's put our line on here again, y equals B0 plus B1x. So again, we just talked about B1. There's our hypothesis test to see if there is some kind of correlation. What B0 tells us is kind of like the intercept. So this is when x is 0. You know, if x is 0, 0 times anything is 0, so this whole thing will get canceled, right? It goes away. And all we left with is our response variable equals whatever our B naught is. And the way that applies, and it doesn't always work, because there'll be some times where it doesn't work, and you'll know when it doesn't work. It'll make sense logically. You know, if you're doing regression line of weight of cars, well, your car is never going to weigh 0, so therefore your intercept doesn't really make any sense in that case. But it can make sense, right? So what if our regression line is how many alcohol drinks versus your blood level, alcohol blood level, right? Well, if I drink 0 drinks, my alcohol blood level will be whatever my B0 value is. And then every alcohol drink I have, 1, so X can be, 1, 2, 3, how many drinks I'm having. I'll have my baseline, my B0, and I'll be adding to my alcohol blood content based on whatever my B1 value is. So that's how B naught helps you. So 0 will cancel out my B1, and I'll look kind of like at the steady state, a baseline. And then my X will change, either increase or decrease, and the B1 will have an effect on the whole regression line. Now, that all comes back to this, though, right? We have to do this hypothesis test to see if our B1 is 0. Because if our B1 is 0, then it really doesn't matter what you put in for X. Therefore, our regression line is not really any good for anything. All right, so regression is very beneficial in statistical analysis. We are just learning the basics on what we can do with regression, but it is something that is used a lot in the real world. I wish we had more time to spend on it. There is plenty of other college classes that get way deeper in the different types of regression, because there is more than just linear. But I wanted to at least kind of give you the basics, because we're going to use a lot of technology to do most of our calculations. And I want you to be able to see when we have good regression lines and when we have bad ones. Always pay attention to the scope of your regression line. It should be within the confines of your data. So like your blood alcohol content, right? If we take samples, 0 to 12 drinks, then our regression line should be between 0 and 12 drinks. So we can't use our regression line and say, what if someone had 100 drinks? This would be the blood alcohol content, right? Because it's out of the scope of what's really going on. And that's how you find predicted values for this. You can take an X value that's within inside the scope of your analysis, substitute into your equation, and you can make a prediction. However, again, it comes back to this key concept. You have to have a slope parameter. You have to have correlation. If you do not have correlation, then your regression line is not a good line for predictions. And according to our book and a lot of other books, the best prediction then would just be take the mean of the Y variables. It really doesn't tell you a lot, so I would, in real life, actually find a different model versus just taking the average of our Y values. But for our course, that will be the solution we'll use. So if there is a correlation, you can use your line to make predictions as long as it's within the scope of your data. If there is no correlation, then the best method currently, until you get into more advanced statistics classes, is to take the mean of your Y variables. If you have any questions, please email me. I will post a video again later in the week showing how to use technology to kind of do some of the calculations, while this video is mainly kind of the theory behind regression for our course. Have a good week.